Okay, so today we're going to learn about sample spaces, events, and probability. There's a few vocabulary words we want to make sure we understand. First one's an experiment. It's any observation of a random experiment or incident. Outcomes are the different possible results of the experiment. The sample space is going to be the set of all possible outcomes for an experiment. An example of an experiment is going to be like observing the results of flipping a single coin. Now, when we flip a coin, there are two possibilities. There's the head of the coin. See if we can get it out of, there we go. And heads. So we can get tails or heads. So those are the two possible outcomes for flipping a coin. So our sample space would be the set head, comma, tail. And then we have the intuitive meaning of probability means that if it's at 0.0, it's impossible for it to happen. And at 1.0, it's certainly going to happen. And then there is a 50-50 chance of it occurring would be 0.5. If it's between 0.0 and 0.5, it's not likely to occur. But if it's 0.5 up to 1, it's likely to occur. So the probability of an outcome in a sample space is a number that is going to be between that 0 and 1. And it's inclusive, which means it includes 0 and it includes 1. P of E is the probability of an event E. It's defined as the sum of the probabilities of the outcomes that make up E, which would be the event. P of F, given that E occurred, is the conditional probability of F given E. So that's F, the line means given that E has occurred. The probability of event F given that E has already occurred. So those are your words right there of what I'm saying. They're in your handout. Basically, it means that you know something else has already happened. Note that the outcomes are conditional on the results of the previous flipped coins. So the probability of E is going to be equal to the number of outcomes in the event divided by the number of outcomes in the sample space. So it's N of E divided by N of S. Now a standard deck of cards has 52 cards. There's 4 suits, which are hearts, diamonds, clubs, and spades. Those are the 4 suits. These are things you need to know. Now, half of the deck are going to be red cards, and half of the deck will be black cards. Also in a deck of cards, we have a jack, queen, and king. Those are what we call face cards because they have a face. There's a jack, queen, and king of clubs, a jack, queen, and king of spades, a jack, queen, and king of diamonds, and a jack, queen, and king of hearts. So our number cards, which would be ace through 10. Now I know when you play cards, the ace can also go at next to a king if you play like poker or something and you're looking for a straight or a flush or something like that. The ace can go up there. But when we're counting, it would be ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. It stops at 10. That would be the number cards. So there's 10 number cards in each suit plus 3 face cards. So each suit, each set of diamonds has 13 cards, a 10 number and 3 face cards. Hearts would have 10 number cards and 3 face cards. And so would the clubs and so would the spades. So those are some basic things you need to know. If you understand that there are 4 suits and you remember there are 52 cards, if you divide 52 by 4, you get 13. So that tells you there's 13 cards in each suit. So just a little bit of information about cards. We've talked a little bit about coins. Let's also talk real quick about dice while we're at it. So dice, when they just talk about tossing a dice, they're talking a 6-sided dice. These are two different colors of a six-sided dice, and we call that because there are a total of 6 sides, 1 through 6. And sometimes in the experiment, they might say you've got a blue dice and you roll a red dice. Now, if it doesn't say 6, you can assume it's 6, but sometimes we can have dices that are of different, how big they are. I think this one has 20 sides, and this one has 9 sides, maybe 10. Nope. I think it's 10 sides because it includes a 0. So this is a 10-sided dice, and I think this one's a 30-sided dice. So if it's something other than a regular 6-sided dice, they're going to state you roll a 30-sided dice, or you roll a 20-sided dice, or a dice that has 8 sides, that kind of thing. But if they just mention dice, they're talking about this. And we're talking about like rolling them and what is the probability of getting what we do. And then we'll talk about other things as they come up in throughout the problems. All right, so our first example, we have a box of 20 gumdrops was found to contain 6 lemon, 5 orange, 2 cherry, and 7 grape gumdrops. Assume that each gumdrop has an equal chance of being selected. If one gumdrop is drawn from the box, what is the probability of drawing a cherry gumdrop? So if the numbers don't match that are in my bowl, but what we're talking about is if I pull out a gumdrop, these are marbles, but if I pull one out, what's the chance of getting a particular kind? Because there's going to be different ones in there. All right, so let's go to a little bit of some writing for some math. So this is 8.1 in our textbook. So for example 1, we have a box of 20 gumdrops, and we want to know what the probability is of drawing a cherry. So for the cherry, I'm going to find the probability of my event will be the number of the E over the number of the S, which is the little formula that we looked at. So in our problem, box of 20 gumdrops contains 6 lemon, 5 orange, 2 cherry, 7 grape. So my event is dealing with cherries. So 2, the total sample is the box of 20 gumdrops. And then I can reduce that. They both divide by 2. I get 1 out of 10. Excuse me. All right, let's look at another question. The second one is the probability of drawing a grape. For drawing a grape, it says that we are doing the same thing. We've got the probability of E will be equal to the N of E over the N of S. Now in our problem, to draw a grape, we had 7 grape gumdrops. So this will be equal to 7 out of 20. And this one won't reduce, so we are done. Okay? All right, example 2. A circular spinner is divided into 19 sectors of equal area. 7 red, 2 blue, 6 yellow, and 4 green. Consider the experiment of spinning the spinner once. Find the probability of that the spinner lands on blue. So if we're talking about a spinner, I'm just going to kind of, if we had a circle here and we spin it, that's what we're talking about. Like so in one of your games that you would have grown up with, you spun to see how many you would go or what color you're going to land on. That's what we're talking about, a circular spinner. All right, so for example 2, we are looking at the probability of E equal to the N of E over the N of S. And we wanted to know what's the probability that it lands on blue. So in our problem, we have 2 blue out of 19 sectors. So this will be 2 out of 19, and that's all we got to do. All right, example 3. An experiment consists of drawing 1 card from a standard 52-card deck. What's the probability of drawing an 8? So this will be example 3. And we're looking at, again, the probability of E equal to the N of E over the N of S. Now, how many 8s? Because that's what we're talking about is 8s are in a deck. Well, there's 1 8 in each deck, or in each suit. There's 4 suits, so there's going to be 4 8s. So there will be 4, and the total number of our sample space is 52 cards. 52 divides by 4, so we'll end up with 1 out of 13, would be the probability of drawing an 8. All right, example 4. An experiment consists of drawing 1 card from the standard deck. Find the probability of drawing a red 5 of spades. All right, let's talk about that. So we're talking about a red 5 of spades. So when we were looking at our cards earlier, we're talking about a number card because we're talking about 5, so it's not in the face cards. But we have 2 red suits and 2 black suits. This is a spade. Spades are black. This is red. This is a red 5, but it's not a spade. You cannot have a red 5 of spades because the spades are black cards. So what is the probability of a red 5 of spades? Well, again, we're going to have our P of E is equal to the number of E out of the number of S. Well, there are no red 5s of spades, so that would be 0 out of 52, which will just be equal to 0. We can divide 0 by anything. We can't divide anything by 0. Right? Example 5. In a family with 8 children, excluding multiple births, that means they didn't have any twins or triplets, what is the probability of having 8 girls? Assume that a girl is as likely as a boy at each birth. So we're looking at if we have a child, the likelihood is you either get a girl or a boy. So there's 2 possible outcomes for each child, just like there was for flipping a coin. There's 2 possible outcomes. So the total possible outcomes would be, so this would be example 5. On a deck of cards, we knew there's 52. On a dice, we know there's 2. But on this, because we're having 8 children, we have to figure it out. So the total possible outcomes will be equal to the amount of times it can happen. So there's 2 possibilities, and that happens 8 times. So 2 times 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 2. 1, 2, 3, 4, 5, 6, 7, 8. And we're multiplying those possibilities. So we could also write this as just as 2 to the 8th. And 2 to the 8th gets us 256. So what's the probability of getting all girls? The only probability to get everyone a girl is one way, because that means every one of them had to be a girl. Otherwise, one of them ends up being a boy, and then you don't have all girls. There's only one way to get all girls, just like there'd be only one way to get all heads or all tails. All right, so we look at our P of E, is equal to the N of E divided by the N of S, would be 1 opportunity to get a girl, and our sample space is 256. All right, our next question says, in a family of 9 children, excluding multiple births, what is the probability of having 8 boys and 1 girl? In any order. Assume that a boy is as likely as a girl in each birth. All right, so this will be example 6. Now we have 9 children with 8 boys and 1 girl. So our N of S is going to be 2 times 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 2, which you get in 2 to the 9th. Now you don't have to write out all those 2's. You can just say, hey, this is going to be 2 to the 9th because it's going to be 2 multiplied 9 times. And that gets us 512. So that's our N of S. Now our N of E is the number of 8 boys and 1 girl. So how many different ways can we get 8 boys and 1 girl? Let's see what we got here. I'm going to kind of demonstrate this with another manipulative. So we've got 1, 2, 3, 4, 5, 6, 7, 8 boys. And we'll do the pink for the girl. Yes, they're stereotypical colors, but we're just going to go with that. All right, so if we're having 8 boys and 1 girl, but they can be in any order. So this would be one way. That would be 2. This would be 3, 4, 5, 6, 7, 8, and 9. So basically what's happening, let me kind of separate these out so that the pink can fit in the middle, is the girl can be born first, second, third, fourth, fifth, sixth, seventh, eighth, or ninth. So that's what they're saying, doesn't matter the order. So that means there's 9 different ways that that baby girl can be born in the family. Another way, if we don't have some manipulatives to draw it out, we can write it out. So we would have 8 boys and 1 girl. Or we could have 7 boys, a girl, and then a boy. We could have 6 boys, a girl, and then 2 more boys. We could have 5 boys, the girl, and then 4 more boys. We could have 4 boys, the girl, and then 5 more boys. We could have 3 boys, the girl, and then 5 boys. 1, 2, 3, 4, 5, 6, 7. Oh, I think I drew too many boys there. Yeah, sorry about that. I was counting too many. So we got 3 boys, a girl, and then that's 4. We need 5 boys here. All right, and then we could do 2 boys, a girl, and then 6 boys. And we could have the boy and then have a girl, and then we could have 7 boys. Or we could have the girl and then have 8 boys. So this would be writing it out where the girl was here, then she was this one and that one, and we still get 1, 2, 3, 4, 5, 6, 7, 8, 9 different ways that we can have this one girl. So the probability of E will be the N of E divided by the N of S, which would be 9 ways to have 8 boys and 1 girl out of a total of 512. Okay, so that would be our answer because it doesn't reduce. All right, example 7. A store carries 4 brands of CD players, J, G, P, and S. From past records, the manager found that the relative frequency of brand choice among customers varied. Which of the following probability assignments for a particular customer choosing a particular brand of CD players would have been rejected? So remember that the probability, it's right over here, the probability of everything has to be between 0 and 1. All right, so let's go look at doing some math here to see which ones might be rejected. So for the first one that we have for part A, we're going to add up all of our numbers to see if our whole entire probability is adds up to be 1, because all of our probabilities have to be between 0 and 1, and the total of probabilities equals a total of 1. All the possibles will have to be equal to 1. All right, so the probability of S is going to be 0.35 plus 0.25 plus 0.22 plus 0.18. And I'm getting this off of our P of J, P of G, P of P, and P and S. Okay, so that's all of them. So this is out of the total. It adds up to be 1. Well, the total equaled 1, so we are good. For the second set of numbers, we have 0.35 plus 0.47 plus 0.44 plus 0.52. So this again is our probability of our event happening here. This ends up being 1.78. That's greater than 1. So this won't work. And then if we look at the third option, we have 0.28 plus negative 0.16 plus 0.25 plus 0.63. And when we add that up using our calculator, we get a total of 1. But there's a problem with this one. All of our probabilities have to be between 0 and 1. This is a negative value, so it makes this invalid. Even though that the total probability equal to 1, the fact that we have one of our probabilities out of the range of 0 to 1 makes that one invalid. So the only one that will work is A. All right, and on your handout, again, I have a little note. The probabilities of all events should be between 0 and 1. And the sum of all of them of an event should equal 1. All right, example 8. A store carries 4 brands of DVD players, J, G, P, and S. From the past records, the manager found that the relative frequency of brand choice among customers varied. Using the given probability values for each of the 4 brands, find the probability that a random customer will choose brand J or brand P. So we want to figure out what's the probability of choosing brand J or brand P. So this will be example 8. Our P of E will be equal to the P of J plus P of P, because it can be either one. It's not this one or doing this one. It's drawing either one. They can choose either brand J or brand P out of all of the possibilities that we have. So the probability of brand J was 0.31 in our word problem, and the probability of P is 0.23. This will get us 0.54. So the probability of them picking either one of these brands is 0.54 out of 1, which would be like 54%. All right. Example 9 is a small combination lock on a suitcase that has 2 wheels, each labeled with 10 digits from 0 to 9. If an opening combination is a particular sequence of 2 digits with no repeats, what's the probability of a person guessing the right combination? All right, so I need to get an example of that, of what that looks like. Let's see if we can kind of improvise. So they're talking about wheels. They're not talking about wheels that are circles this way, but they are wheels like this. So if I have a combination lock, like on, maybe you had one at school that was a combination lock, or on a fence, or on a luggage piece, something like that, where you can spin the wheels to a certain number, and then it will pop open. And as you spin that wheel, you're getting a different number that occurs. So they're looking at, they want to know how many different ways this can happen. Now, you can't repeat the numbers, so if you can't repeat them, the choice decreases with each wheel. So this will be example 9. So we got to find out how many are in our sample space first. So on the first wheel, we have 10 digits that go around. So we have 10 to choose from on the first wheel. On the second wheel, because we cannot repeat whatever number we chose. If we chose 1 here, we can't use 1 over here. If we got a 5 over here, we can't use 5 over there. So it can't repeat. So there's only 9 numbers left. So there's 10 on the first dial, and then there's 9 left on the other one. There's still 10 there, but you can't use whatever number you use here. And this will get us a total of 90. So we're multiplying just like we did when we were doing the number of children, where it was 2 times 2 times 2. But with babies, it can repeat. On here, they're saying you can only use that digit 1 time. All right, so now our probability of the event will be how many times that occurred out of the total. Now, we're looking at a 2-digit code, and it's a particular one. So it's not going to repeat at all, so there's only going to be 1 of that particular code out of a total of 90. So what's the probability of a person guessing the exact combination? 1 out of 90. All right, we're on to number 10. So on number 10, we have an experiment of tossing 8 fair coins. Fair coins means they are equally likely to toss heads or to toss tails. Sometimes there's coins that are not fair, so they more likely go for either the heads or the tails. But these are a fair coin. One of the coins has a head on both sides. Compute the probability of obtaining 8 heads. So one of those has a head on both sides, so it's going to occur to be heads every time. All right, so we got to go figure out some math here. So again, if we want to get all heads, because that's what it said, compute the probability of obtaining 8 heads. There's only one way, right? Because as soon as one coin gives you a tail, you don't have all heads. So we've got to find our number of S because we know the number of E has to be 1. There's only one way in this event to get all heads. Otherwise, we're going to get a tail. So the N of S is going to be that 2 times 2 times 2 times 2 times 2. One, 2, 3, 4, 5, 6, 7. Now, I'm only doing 7 of those because one of the coins only has one answer, right? It's a two-headed coin. So there's only one outcome for that. It doesn't have two outcomes. It has one outcome. So I have 7, 2 times 1. Well, times 1 won't change it at all. So this will be 2 to the 7th, which is 128. With that double-headed coin, it only has one outcome. It no longer has two outcomes. So our probability of E will be equal to the number of E out of the number of S, which will be 1 out of 128. That's the likelihood of getting all heads when flipping those 8 coins. But one of them has a double head. All right, number 11, we're going to roll some dice. An experiment consists of rolling 2 fair dice and adding the dots on the 2 sides facing up. Using the sample space provided below and assuming each simple event is as likely as any other, find the probability that the sum of dots is 8. So we are looking for the adding of this to be 8. That means we can get 6 and 2. We have a couple of options here. We can get 3 and 5. We can get 4 and 4, right? Those all add up to 8. And then it would go the other way. We can have 5 and 3. We can get 6 and 2. Now, why can't I use the dice if it rolled a 1? So we're using 6-sided dice. There is no 7-sided. So you can't use 1 to get a 6. You can only use the other ones. So if I kept rolling, I could have a 5 on this dice, and I could have a 3 on this one. I could have a 6 on this one and a 2 on this one. So I don't have any more blue ones. That's why I put these both as red. Whoops, and you can't see everything. Let me scooch it up. So it doesn't matter if we roll the 2 first or the 6 first. And again, you still can't see, Mom. There we go. So it doesn't matter if we roll the 2 and then the 6 or the 6 and then the 2. These are the different ways we could add up to get 8. 1 cannot be used because, like I said, we don't have a 7-sided dice. So how many different ways are there to get a dice that adds up to 8? There's 1, 2, 3, 4, 5. Now, you may not always have the things that I have to write these out. So I'm going to show you how you could do this on paper. So for an example 11, we're looking at the number of E. We would have 2 and 6, 3 and 5, 4 and 4, 5 and 3, and 6 and 2. So here I am doing the same thing I just did, pulling the dice out, but showing you can pair them up the same way. This would be the roll on one dice, the roll on the second dice, which tells us that there are 5 ways for this to happen. Now, for our N of S, we have the first dice that has 6 sides, and the second dice also has 6 sides. They didn't tell us, like on that spinning wheel, where we couldn't have the same number repeating. They didn't say anything about that. So I have 6 times 6 equal to 36. Because they didn't say we couldn't repeat, I don't have a decrease on one of those. You just get to count on both, kind of like with flipping a coin. And part of that is depending on just how they word the problem. All right, so we've got the probability of E equal to the number of E over the number of S, which would be 5 ways that we can roll an 8 out of a total 36 different ways that you can do this. Now in there it said to use this sample space, and you can use the sample space, and that's just what I have here. And if you look at it the way that it's drawn out, you've got like 6, 2, there's 8, 5, 3, 4, 4, 3, 5, 2, 6. So if you use this as you're working on your homework and such, this one adds to 2. These 2 that are now touching the pen add to 3. This diagonal adds to 4. This one adds to 5. The next diagonal adds to 6. Then we add to 7, and then 8, and then 9, and 10, 11, and there's one way to roll 12. So that can kind of help you out as far as if you're trying to figure out exactly what you're looking for. All right, so that's number 11. Let's go on to number 12. Number 12 is an experiment consists of rolling 2 fair dice and adding the dots to the on the two-sided facing up. Using the sample space provided and assuming each simple event is as likely as any other, find the probability that the sum of dots is less than 5. So we're talking less than 5, not equal to 5, but less than 5. So if we're looking at example 12 and we want it to be, we're going to roll less than 5. Our event, the number of ways it can occur, I could roll 2 1s. I can roll a 1 and a 2. I could roll a 2 and a 1. So 1 and 1, that's 3. That's a 2 and a 1. Does it say less than 5 or less than 4? Let me double check. It says less than 5. My handout or my notes say 4, so we're going to go with the handout. I can also have a 1 and a 3. I would have put these in other order if I had realized that. So less than 5, because I can add up to 4. So that's 2, that's 3, that's 3, this is 4. I can get a 4 with a 2 and a 2, and I can get a 4 with a 3 and a 1. Now what I would have done, because I tried to do these in a better order, I would have done 1 1, 1 2, 1 3. Then I would have gone on to 2. I try to do it in an orderly fashion so that we don't jump around. And then 2 2, that would get us up to 4. And then I would go to the 3 and do the 1. There's nothing wrong with writing it that way, but I prefer to be a little bit more orderly of doing the 1 with the 1, the 2, and then the 3, then going to the 2s, going to the 1 and the 2, and then going to 3. Just because if you do it in a patterned way, you don't miss one of your possibilities. All right, so rolling less than a 5, we're now looking at our probability of E is equal to the n of E over the n of S. We have 1, 2, 3, 4, 5, 6 ways to do it. And that's out of 36 possible outcomes. They both divide by 6, and we will get 1 out of 6. All right, example 13. An experiment consists of rolling 2 fair dice and adding the dots on the 2 sides facing up. Find the probability of the sum of the dots being less than or equal to 12. Being less than or equal to 12, the sum of whatever's on the dice. Well, my highest dice I can roll are 2 6s. 2 6s equals 12, right? That means all of the dice below it, no matter what I roll, will be less than or equal to 12. We can also go back and look at our sample space. The highest sum I showed you was 12. The rest is 11, 10, 9, 8, 7, 6, 5, 4, 3, and 2. They are all less than or equal to 12. So that means that our probability, this will be for example 13, our probability of the event is the number of the event over the number of the sample. So I can roll my dice 36 different ways, and they're all going to be less than or equal to 12 for a sum, and there are 36 different ways I can roll them, so my probability equals to 1. All right, example 14. Each of the two computers randomly generate a number between 8 and 13. Then finds the sums of the two values. Using the sample space below and assuming each simple event is as likely as any other, find the probability that the sum is divisible by 4. So on this, I want to see what my sums are. I want to see, do I have anything that adds up that's divisible by 4? So if I'm looking for that, I'm looking for a sum that's a multiple of 4. If it's going to divide by 4, it has to be a multiple of 4. So we'd be looking like for 4, 8, 12, 16, 20, 24, 28, multiples of 4. So as we go through our list here, we're going to look for the ones that will divide by 4 for the sum. So this is example 14. So we're starting with 8, so we know we won't have a total of 8. So the lowest one is going to be 8 and 8, and we're going to end at 13, 13. So 8 plus 8, well, that equals, we'll get us 16, and that divides by 4. It equals 4. So this would be our 8, 8. 8 plus 9 is 17. 8 plus 10 is 18. 8 plus 11 is 19. 8 plus 12, that'll get us 20. So we have 8, 12. So 8 plus 12 equals 20. Divide by 4, we get a 5. 8 and 13, that'll be 21. 9 plus 8 is 17. 9 plus 9 would be 18. 9 plus 10 would be 19. Looks like we go over here now. So 9 plus 11, that would be 20. So we're going to have 9, 11. And I guess, why don't we stay in this row? We'll do this row, we'll do this row, and then we'll go. That way it's more systematic. All right, 11 plus 8, that would get us 19. 11 plus 9, that's 20. Divide by 4 will get us 5. 11 plus 10, 21. 11 plus 11 is 22. 11 plus 12 is 23. 11 plus 13, that'll get us 24. Divide by 4 will get us 6. 12 plus 8, that'll get us 20. 20 divided by 4 will get us 5 again. 12 plus 9 is 21. 12 plus 10, that's 22. 9 plus 11, that's 20. Let me switch colors. All right. 9 plus 12 is 21. 9 plus 13 is 22. 10 plus 8 is 18. 10 plus 9 is 19. 10 plus 10, that would be 20. Divided by 4 equals 5. 10 plus 11 would be 21. 10 plus 12 is 22. 10 plus 13 would be 23. 12 plus 11, that would be 23. 12 plus 12, that would be 24. That would get us a 6. 12 plus 13 is 15. 13 plus 8, 12 plus 13 would be 25. 13 plus 8 would be 21. 13 plus 9 is 22. 13 plus 10 is 23. 13 plus 11 would be 24. 13 plus 11 equals 24. Divide by 4. Again, will get us 6. Then I have 13 plus 12 would be 25, and 13 plus 13 would get us 26. Now, I chose the ones, these will all work. I was adding the numbers and saying that doesn't work, but how do I know? Let's go back to the beginning. If I picked 8, 9, I would have 8 plus 9 equals 17. And if I divide that by 4, I don't get a whole number. So if you're not great at your multiples, you can use the calculator. We would have 17 divided by 4 would get us 4.25. Well, that's not a whole number, so it doesn't divide evenly by 4, so that's why that doesn't work. Where the rest of these all divided evenly by 4, and that's why we could choose those. All right, so how many of these worked? We got 1, 2, 3, 4, 5, 6, 7, 8, 9. So now our probability of our event is going to be the number of the event out of the total of the sample space. So we found 9, and how many total did we have? Does it tell us how many we have? It just says it's this, so we've got to count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That means there's 9 here, 9 here, and 9 here. Well, 9 times 4 would get us 36 possible outcomes. So 9 out of 36 will get us 1 out of 4 when we reduce it. All right, example 15. In order to test a new drug for adverse reactions, the drug was administered to 1,000 test subjects with the following results. 80 subjects reported that their only adverse reaction was a loss of appetite. 90 reported that their only adverse reaction was a loss of sleep. 600 reported no adverse reactions at all. If this drug is released for general use, what is the probability that a person using the drug will suffer both a loss of appetite and a loss of sleep? So we're looking at both a loss of appetite and a loss of sleep. All right, so we're going to write a few parts of this down. So this will be example 15. So our sample space, they told us that there were 1,000 subjects. It said 1,000 test subjects. Just equals 1,000. Now, the N of a loss of appetite, we're going to call that N of A. There were 80 that lost their appetite. There were some that loss of sleep was their side effect. So we're going to call that the N of L, because that's what they did in the book. And that was 90. We can't use sleep because we're already using N of S for the sample space, so they went with L. Now some had none. They didn't have any issues, and that was N of C equal to 600. So let's read our problem one more time. So we're testing the drug for adverse reactions. There were 1,000 subjects with 80 reporting their only adverse reaction was appetite loss. 90 was a loss of sleep. 600 reported no adverse reaction at all. If the drug is released for general use, what's the probability that a person using the drug will suffer both the loss of appetite and a loss of sleep? Now, they didn't say there were any more losses. They didn't say, hey, there's another loss out there. These are the only ones they talked about. There was no loss, there's a loss of sleep, and a loss of appetite. So that tells us that there are some that we got to take out all these because the rest of the people would end up with both. So we're going to call this the number of both. Both are, so we're going to call it B. The number of both would be the ones that had appetite and sleep as an issue. So that means we're going to take the entire sample space, subtract out the appetite loss, subtract out the sleep loss, and subtract out the ones who had no loss. So this will be the total of 1,000 minus the 80 patients here, or the subjects, they weren't patients, the 90 there, and the 600. And that'll get us a total of 230. That's what's left over out of the 1,000 people that only had one reaction or no reaction. That means the rest of them had to have both reactions. So now we can find the probability of both would be the N of B over the N of S, which will be 230 over 1,000, because that's a total of subjects. This is the ones for the total of both, and that'll get us 0.23. In your homework, they're looking for like a decimal answer there. All right, so that is our start to our probabilities with our sample spaces, events, and probability. Make sure you're understanding all of this because we're going to be using many of these things throughout this section of material.